Okay, welcome all. So in the second lecture of this week, we are going to review the aspects of time-independent perturbation theory, and we will see the development of the formulation of first-order perturbation theory and what kind of corrections they lead to. We will also dwell with higher-order corrections in this setting, and we will do so by examples of a couple of simply known systems like harmonic oscillators or hydrogen atoms. So this is the mandate for today's discussion, and let us get going with the discussions of the perturbation theory. In the previous class, we have learned that the time-independent perturbation theory takes into account for a correct description of nature, and it puts terms which are typically weaker than the strongest term which we consider in our understandings. For example, if there is a harmonic oscillator whose Hamiltonian in the free case is given by the first two terms p square by 2m naught plus half kx square, then as we discussed in the previous class, we do not really know if there is a scope or not of additional higher order terms depending upon the shape of the potential. If I try to move away from the minima, we have seen that higher order terms can in principle be present for arbitrary potentials. Similarly, there could be a scope for a higher order momentum dependency coming from the correct description of kinetic energy which is allowed in the special relativity. All these examples we had discussed in the previous class, and in this class we are going to develop formalism to how to handle these correction terms once we are certain that they are present. So for today's discussion, we are focusing on time-independent perturbation theory. By that, I mean there is no explicit dependence on time in the Hamiltonian which is introduced into the free part. For example, in the harmonic oscillator case, when I allow for cubic order or quartic order correction terms, that Hamiltonian does not explicitly depend on time. These coefficients alpha or these coefficients 8m naught cube c square for the fourth order momentum corrections, they are not supposed to contain any dependence on time explicitly. So the whole Hamiltonian can depend on time implicitly through the positions dependence on the time, but that is not a direct dependence, that is an indirect dependence. So therefore the partial derivatives are 0 with respect to time. Total derivatives may not be 0 because the total derivative will account for the change of the Hamiltonian with respect to the position, and then the positions change with respect to the time. So clear demarcation of a time-independent Hamiltonian would be its partial derivative with respect to time should be 0. Okay, so overall, as we have seen, depending upon higher order correction terms in the potential or higher order correction terms in the kinetic term, we typically end up with a structure like whatever was our free theory. By free theory, I mean the system which we had exactly solved. For example, harmonic oscillator, this piece was the free theory. For hydrogen atom, hydrogen-like atom, this was the free theory. Now, there is an extra term which is added to it, which is lambda times h1, where lambda is a parameter which tells you about the strength of the term which is coming about. This usually depends upon the parameters in the theory. For instance, as we have seen in the arbitrary shaped potentials minima, if you remember the discussions in the previous class, the higher order terms dependent on the third derivative of the potential at the minima. So the parameter alpha which I have written about in the present day slide, in today's slide, that alpha is virtually the third derivative of the potential at the minima. Similarly, for the fourth order momentum correction coming from the correct description of kinetic energy comes with a parameter 1 upon 8 m naught cube c square. That is the mass of the particle times the speed of light and their various powers. So these are the parameters which tells us that certain new operators are coming along with a coupling parameter lambda. For the first case, the operator part h1 is x cube, while the coupling parameter part lambda is alpha, while for the second part, the operator in the new Hamiltonian is P4, while the coupling parameter lambda happens to be minus 1 upon 8 m naught q c square. The minus sign is here as well. So in this way, we are supposed to solve a problem of a renewed Hamiltonian, a new information that we know has a right to exist. Previously, we had solved for H naught alone. Now we know that the correct description does not contain H naught alone, but there is a possibility of a new term which comes with some coupling parameter lambda. So we will go ahead with a general lambda, and in case by case basis, we will see what lambda happens and how much of the correction it leads to. So the idea at hand is we need to solve the correct Hamiltonian, which is made up of two pieces, H naught and lambda H1. And we want to know what are their eigenstates. Previously, we used to know the free theory is Hamiltonian. By free theory, I mean none of the correction terms were allowed. I knew the solutions of this. For instance, I knew what are the eigenstates of ordinary harmonic oscillators and what are their eigenvalues. Similarly, I knew what is the correct energy eigenstates of ordinary hydrogen atom without the higher order correction and their eigenvalues. Now I know there are more terms than the usual terms which we have solved for. So then I need to go back and solve this equation again and try to get a renewed information of what are the states which are correctly describing the physics of harmonic oscillator around arbitrary potential, or correct description of kinetic energy in hydrogen atom, or mixing of both. Even in harmonic oscillator, the p squared term can be corrected by presence of a quartic p4 term coming from special relativity. All right. So the idea is we will develop the game for H, the total Hamiltonian being made from the free part and the perturbation part. And I know that once I have changed the Hamiltonian from being just H naught, the correct eigenstate can no longer be only psi n naught. Psi n naught was eigenstate of H naught. It can rarely so happen that it is also eigenstate of the full H. Unless H naught and H1 commute, it is not going to be that case that psi n naught is also an eigenstate of the full H as well. So the correct eigenstate psi n should be different from psi n naught. So therefore, there should be correction terms, and we allow for corrections terms to be expandable in the parameter lambda, whatever is the coupling parameter. It could be first order in lambda times some correction term plus second order in lambda, which is lambda square, and correction term at the second order, and so on. Similarly, the energy eigenvalues I used to know for the free theory. In the correct description of the theory, when I have added the extra term, E n naught can no longer be the eigenvalue of the system. So therefore, this has to be corrected as well. So therefore, we would add extra terms with a power series expansion in lambda. I have added a linear order terms in the H1. This is the coupling parameter. But I do not know if the effect of lambda will only remain in the wave function at linear order or in the eigenfunction in the linear order. This I need to check and prove. So in principle, I'm allowing for a power series expansion in the unknown things which are wave function and the energy eigenvalues. So there I am not sure if the corrections are only order lambda. They can be order lambda square or higher orders as well. So therefore, the picture is that we have to solve for a corrected expression or equation, which is new Hamiltonian, which is H naught plus lambda H1 times the new eigenfunctions, which is previous eigenfunctions plus correction terms, is equal to new eigenvalues, which happens to be previous eigenvalue plus correction terms, and the new eigenfunctions again, which we have wrote down as previous eigenfunction plus correction terms. Now, it is very important to note in this description, we are assuming that these corrections terms psi n1, psi n2 they are already orthogonal to the previous eigenstates. Whatever we are adding to the previous eigenstates, those corrections are perpendicular or orthogonal to the previous eigenstates. So these are the correction terms. Okay, in vectorial description, if this vector was your eigenstate initially, then there are some minute terms which are added in the perpendicular directions such that a shifted vector becomes a correct eigenfunction. Now, why do we need to do that? Why do we need to assume that the corrections terms are orthogonal to the previous eigenfunctions? This can be checked in the linear order perturbation theory as follows. So suppose we look at the first order correction term, which comes with single power of coupling parameter lambda. So we are going to focus on the first order correction. Suppose psi n1 is not orthogonal to psi n0. That is, the unperturbed eigenvalues, eigenvectors are not orthogonal to the newly corrections. So these new corrections can also be projecting. They are not completely orthogonal to psi n0, so they could have some projections along psi n0. Since this is just a wave function, and a wave function can be decomposed in the basis of the eigenfunctions of a Hermitian observable, which was Hamiltonian, so I can write this wave functions into the superpositions of all the previous eigenfunctions. So psi n0, psi l0, where L runs from 1 to infinity. So in this decomposition, if psi n1 is not orthogonal to psi n0, there will be one term which will be along psi n0. So this will be the term. Suppose it is allowed. I know under my perturbation theory, the correct description of eigenfunction goes from being only psi n0 to psi n0 plus first order correction term. Up to first order, this is the correction. If I want to include the second order term, then there will be lambda square psi n2 as well. But up to first order, this psi n1 tells me the correction to the wave function. So therefore, this is psi n up to first order. Now this psi n up to first order can be collected as, because this psi n1 we have already decomposed in a series with terms not equal to n and one term which is equal to n. So what I will do, I will just collect the coefficients of different eigenbases. So in this psi n1, all the bases are being summed over, and there is one term which is also psi n0. So therefore, the renewed corrected eigenfunction will be the previously existing eigenfunction coming with coefficient 1 and lambda times CNN, which is here, along the psi n0 direction. So you can see that if psi n1 has a projection along the psi n0 direction, it is going to feed to this 1 which is already existing. And then the remaining term over here will come with a coefficient lambda. So therefore, the full wave function will become 1 plus lambda CNN along the psi n0 direction and lambda times CNL along all other basis vectors direction. Now 1 plus lambda CNN can be pulled out as a common factor, so that inside the bracket I would just be left with psi n0 plus a lambda divided by 1 plus lambda CNN, the common factor which I have pulled out, and the series which is over here. So the wave function, the corrected wave function up to linear order, corrected eigenfunction up to linear order is this. Now I want this to be normalized. That means I should calculate the psi n. If it is not equal to 1, I should divide the wave function by its magnitude, which is this. So if I take this psi n and compute the magnitude of this vector, I am going to get an answer which is this: square root of 1 plus lambda CNN whole square plus lambda square 1 plus CNN whole square. Okay. So just a second, I will get a CNL squared here as well. Okay, all right. Now, this is the answer which is obtained after normalizing the state. So normalized corrected wave function should be this whole expression. But we knew that this expression cannot be trusted more than order lambda because our story started with correction up to order lambda. If I want to include things up to order lambda square or higher powers, I should have started the story with higher powers of lambda as well. So this expression which is over here has to be corrected only up to order lambda. So I should maintain things only up to order lambda. Wherever I see a lambda square, I will throw that out because I had thrown lambda square term from the beginning. There was no lambda square I had considered. So better not to consider lambda square anywhere. So wherever I will see a lambda square, I will throw that term away. For example, here is lambda square, I will just ignore it. Then the square root quantity in the denominator becomes a square root of a perfect square, which will just yield you 1 plus lambda CNN. Now you see, if you do this correction term carefully, this 1 plus lambda CNN, which was outside as a common factor, kills the denominator, and you are left with this series inside, where the summation now does not include L does not include N. And therefore, again, I would do the business of throwing order lambda square terms away. Here is one more term, lambda times this lambda. That will also be thrown out. So I will be just maintaining this term and the first term, lambda multiplying the 1 and then this series. So therefore, the normalized wave function at the linear order is made up from psi n0 plus lambda times this series, where the series does not include the n term. So therefore, in the previous slide, that's what the statement was. If I want to write my corrected wave function up to linear order, it would be the previous eigenfunction plus a correction term which does not include projection along its previous direction. So therefore, for normalized psi n tilde up to order lambda, we only need to compute CNLs. CNLs were where? What? CNLs were the coefficients along the different basis vectors, which does not include the n. N is the eigenfunction for which we are trying to find the corrections. Okay, so that is another way of saying that the correction terms are orthogonal to psi n0. Alright, so with this information, we can proceed further. And now I know that I have a perturbation equation which I can try to pick up terms order by order in lambda. For example, if I go back to this slide and clean things up, so you see on the left hand side I have a h0 plus lambda h1 multiplying the power series expansion of the eigenfunction. On the right hand side I have a power series expansion of energy eigenvalues multiplying the power series expansion of the eigenfunction. So when I open these terms, I will get certain terms in various orders of lambda. For example, h0 acting on this psi n0 will be free from any lambda in the left hand side. On the right hand side, similarly, this en0 multiplying this psi n0 will also be free from any lambda. Now, if I move forward to see how many terms are there with single lambda, there is a possibility that this h0 acts on this part where one lambda comes, or this lambda h1 acts on psi n0. These are the two terms which will come at the linear order of lambda. That is, these terms will come with a lambda multiplication. Similarly, if I want to compare what are the terms which will be arriving on the right hand side with a single power of lambda, it may come again through two ways. First way will be this en0 goes and hits this lambda times psi n1, or vice versa. This lambda times en1 here hits this psi n0. So this is how we will pluck up terms order by order, and we will try to see what do we get at various orders. If I just collect the terms free of any lambda, which is called order lambda to the power 0, as we saw, only one term was there in the left hand side, H0 acting on psi n0, and the right hand side I had the eigenvalue, unperturbed eigenvalue, hitting the unperturbed eigenfunction. So this is the unperturbed equation. Because perturbation comes with a lambda, it is reasonable to expect that if no trace of lambda is considered, then there should not be any change. Fair enough. Now, if I want to see what happens at order lambda to the power 1, that means what are the terms which are multiplying at the linear power of lambda, I get two terms in the left hand side as we discussed, H0 hitting the psi n1 or H1 hitting the psi n0. On the right hand side again there are two terms, En0 hitting the psi n1 and En1 hitting the psi n0. Again, to just remind you of this thing, at the linear order of lambda, either this H0 can go and hit this term and this lambda H1 can go and hit this term. Both these terms will contribute to order lambda terms. Similarly, on the right hand side, either this En0 goes and hit this lambda times psi n1 or this lambda times En1 goes and hits the psi n0. So these are the two possibilities in both left hand side and right hand side, which we have listed down over here in the boxed equation. So now this is an operator equation in which some operators are acting on the state. So let me write as kets. So these are kets and these are operators, and while these are numbers, eigenfunctions correction, so these are just numbers. So since it is a vectorial equation, I can take the projection of the equation along any basis direction. For example, I can hit the whole equation from psi n0 bra from the left hand side. That means I will just take psi n0 and throughout the equation, both the left hand side and the right hand side. When I hit the left hand side, the first term I get is psi n0 hitting the H0 term and psi n1. The first thing on the right hand side similarly I will get is En0, which is a number, it will just go across, and then psi n0 will go and hit the psi n1. Now, one interesting thing to see is that H0 is supposed to be a Hermitian operator. Therefore, H0 hitting the psi n0 from the left hand side will again give me En0 and the psi n0 back. This is the eigenvalue equation for the Hamiltonian, unperturbed Hamiltonian, and that will hit the psi n1. So left hand side, we had obtained En0 times psi n0 hitting the psi n1, and the right hand side also the first term exactly give the same term which has been obtained from the left side. So the first term on the left and the first term on the right after the projection along psi n0 exactly cancel each other. So this will be cancelled with this, which is the projection of this term along the psi n0. And I will be left with the projection of the second term along the psi n0, which is this in the left hand side, and projection of the second term on the right hand side along the psi n0, which here is psi n0, and since this is well normalized state, psi n0, it is well normalized state, this is going to be 1, and therefore we had written only En1 on the right hand side. So therefore, from this projection equation, we just taking the projection along the psi n0, we ended up getting an equation which tells us about En1. The right hand side has En1. This is the first order correction in the energy eigenfunction. So energy eigenfunction, the first order correction has been obtained now. This first order correction will be obtainable if I compute the left hand side quantity. That is, I take the perturbation Hamiltonian and do this computation. I will get to know what is the first order correction. That is the perturbation Hamiltonian squeezed between the previous eigenfunctions. Psi n0s were the previous eigenfunctions, no longer they are eigenfunctions of the new Hamiltonian. Yet, if I take the H1 and take its expectation along this psi n0, then I will get the first order correction to the eigenvalue. Okay. Similarly, if I take the projection with respect to psi L0, where L is different from N, I take this equation, which is true for N, and then I take the inner product with respect to psi L0. Again, in the left hand side, I will get the term which was H. This will come from taking the squeezing of H naught with psi L0. H naught acting on psi L0 will give me EL0, which is this, and I will get the psi L0 psi N1, and then on the right hand, on the second term will be just the perturbation Hamiltonian H1, psi N0 was already there, and then this gets squeezed with psi L0. So therefore, I will get the second term on the left hand side is this psi L0, H1 in between, and psi N0. On the right hand side, when I hit the right hand side with psi L0, the first term, the En0 is just a number, psi L0 will go inside and hit the psi N1. So I will get En0, psi L0 hitting the psi N1 because En0 has come out as it was a complex number or real number. The second term, En1 is also a number, then therefore it will also come out, and this psi N0 will be hit upon from the left by psi L0. So psi L0, psi N0 with En1. Now, since again these are eigenfunctions of the unperturbed Hamiltonian, which was Hermitian, they are supposed to be orthogonal. So therefore, if n is not equal to L, which we have chosen, this will be 0 because they are orthogonal to each other. So the second term on the right does not contribute. I am left with only the first term, which was En0 coming with psi L0, psi N1, this inner product, and the left hand side had two terms. EL0 with the psi L0, psi N1, the same inner product which appears on the right hand side but with a different energy function. Here it is EL0, right hand side it was En0, and the perturbation Hamiltonian is squeezed between psi N0 and psi L0, two different unperturbed eigenfunctions. In first order correction, it is squeezed between the same eigenfunctions from left and right. When I take the projection with respect to psi L0, the first term gets squeezed between two different eigenfunctions, psi N0, psi L0. So what I can do, I can take this left hand side term and bring it on the right such that I will get En0 minus El0 as a common factor for this inner product, and therefore this inner product, which is psi L0 psi N1, will be this much. Okay, remember we had argued that psi N1 is orthogonal to psi N0. It does not have any projection along the psi N0 direction, but it may have some projection along other basis direction when L is not equal to N. So it has some non-zero projection along different directions when L is not equal to N, and those projections are obtained by the squeezing of the perturbation Hamiltonian between the two states N and L and their energy difference which comes in the denominator. I hope this is clear to you. We will do this with an example and try to find out what kind of corrections do come about in different systems. Okay, so let us move on to some example. Okay, just before going to the example, the inner product which we have obtained over here, the inner product between the first order correction along the different basis directions, that can be given a compact name. That is to say, we have realized that psi N1 can be decomposed along the unperturbed eigenstates eigenfunctions, but for the fact it does not contain any projection along its own unperturbed direction. So I would have all the basis elements present apart from psi N0. So it is decomposable in this basis with one basis element missing, which is psi n0. And therefore, the projection which we have just obtained over here, psi L0, psi n1, is essentially these coefficients C and M. So if I compute psi L0, psi n1 by assuming this definition of psi n1, then you get to know that this projection is just giving you the coefficients C and L. So these coefficients are known now from the squeezing of the H1 between N and L and their energy difference. For example, N can be 1, L can be 2, then I will get the Hamiltonian, perturbation Hamiltonians of diagonal element H1, 1, 2. If N is 2, L is 3, I will get the corresponding of diagonal matrix element 3, 2 of the perturbation Hamiltonian. So let us do one example to see this concept in more clarity. So we will take the Hamiltonian of a harmonic oscillator, which is this, and as we know, we can insert a correction term coming from correct description of kinetic energy, which is the fourth power of momentum, which comes as an additional term. Okay, so therefore, this is my perturbation Hamiltonian, and this, the parameter lambda is 1 over 8 mq(c) square. Okay, so I'm just taking the definition of 8 mq(c) square as inverse of 8 mq(c) square as lambda, or I could define a lambda, fictitious lambda here, which will be put as 1 at the end of the day, and then this whole thing will become the operator. So let us go along with this thing that a bookkeeping parameter lambda is inserted, with which we will compare various powers of lambda, and then at the end of the day I will put lambda to 1. Okay, so in that case, as we have discussed, the first order correction En1 is supposed to be the perturbation Hamiltonian is expectation with respect to unperturbed eigenstates. So this is my perturbation Hamiltonian, P4 upon 8 mq(c) square, and if I want to know first order correction in the nth eigenfunction, what I will do, I will take the Hamiltonian, perturbation Hamiltonian, and obtain its expectation with respect to the unperturbed nth eigenfunction. Okay, so let us do this thing in more detail. I know in harmonic oscillator, the operator P can be written in terms of the ladder operators A minus A dagger divided by iota up to some dimensionful constants. This you can look up at any quantum mechanics book. Therefore, the fourth power of that is supposed to come up in the perturbation Hamiltonian. So I will take the whole definition of P from here, take its fourth power and squeeze it between psi n0 from left and right. And that will give me the En1. So this computation is supposed to give me En1. Similarly, if I want to know the projection CNLs is telling me the projection of the first order correction along the Lth unperturbed eigenbasis. So Cn, the subscript n, is telling you about which eigenfunctions first order correction you are looking for. I am looking for first order correction of nth eigenfunction, and the upper index L tells you what is its projection along the unperturbed Lth basis. So similarly, if I want to know CNL for this perturbation Hamiltonian, what I have to do? I have to take this operator, which is the fourth power of momentum upon 8 mq(c) square, 8 mq(c) square, and squeeze it between psi n0 from the right hand side and psi l0 from the left hand side, and divide it by the energy difference of unperturbed system. Remember, CNL where the perturbation Hamiltonian squeezed with respect to psi n0, psi l0 from left hand side, left and right, and the denominator being obtained from the energy difference. In harmonic oscillator, energy difference is just n minus L h bar by omega, h bar times omega, and the upstairs I have this fourth power is squeezed between psi n0 and psi l0. Okay, let us do it for the ground state. Suppose I want to know with this higher order quartic momentum term, what happens to the ground state? N is equal to 0. Previously, I knew that the unperturbed harmonic oscillator's ground state energy is just half h bar omega. Now I want to know, when I have added this kinetic term, p to the power 4, what happens to the ground state energy? The first order correction to that energy is this quantity as we have listed down. I'm going to compute this quantity with n is equal to 0. So it would be a minus a dagger to the power 4 squeezed between n is equal to 0 from left and right. All the constants which were appearing here, here, and here have been combined to get me h square by 2 m square omega square. You should verify this. And ultimately, this is this computation I'm supposed to find out. So I have to open this quantity up and squeeze it between 0 and 0. If you do this exercise, you will find out only this term survives. All other sums in the expansions vanish. And the rules of A and A daggers hitting any particular eigenstates of Hamiltonian are also known for harmonic oscillator. Using these information, you can quickly prove that the first order correction is this much, 3h naught square upon 2m square omega square. En0 was supposed to be for ground state. So this is for n is equal to 0. For ground state, it was known to be, this is half h bar omega. Once I have added first order perturbation, then this gets changed by 3h square upon 2m square omega square. And there will be second order term as well, third order term as well, but up to first order correction, this is the term. Similarly, if I want to know what is the first order correction to the ground state wave function, then I need to compute this C0Ls. The perturbation Hamiltonian squeezed between 0 and the L from right and left, and their energy differences, which will be just minus L. N minus L for n is equal to 0 will just be minus L. So therefore, now I have to compute A minus A dagger to the power 4 and squeeze it between 0 and 1 from the left and right. You can do this computation. You can open up A minus A dagger to the power 4. Ultimately, you will get a hell lot of terms. But this computation will be very simple once you have expanded it out. You will realize that none of these terms survive under the squeezing of 0 and 1 from the left hand side, left and right. So therefore, when none of the terms survive, the overall correction is 0. That means C01 is 0. That does not tell me that there is no correction. It just tells me that it has no projection along the first eigenfunction as well. But it may have some projection along the second eigenfunction, C02. So then again, I have to do the same thing. I have to squeeze the operator between 0 and 2, divide it by their energy difference. Overall, I will get this coefficient. And this time, I will, after this expansions, just like whatever we have done over here, if I put it between 0 and 1, 0 and 2 this time I will get that there is a non-zero contribution which will survive. So this will not be 0, unlike C01. So C02 is not 0. Okay, so this is your exercise to do this computation cleanly and find out what is this box. This is the non-zero number which will survive. So therefore, the new eigenfunction psi 0 ground state, new ground state, is the previous ground state plus C10 times 1, it so happens that C10 is 0, therefore no projection along the first excited state, but second excited state comes as a correction in the correction term. Similarly, you can prove that after that C03 is also 0. The next term which will survive will be C04. So all these terms will appear at the order lambda. As we discussed, lambda would be put to 1 at the end. So once I have put in lambda is equal to 1, the correct description of the wave function up to order lambda, this is the corrected ground state. Okay. So let me stop over here for today and for this discussion. Then we move on to discuss higher order corrections and the second order correction to the system.